For centuries, the ancient Greek philosopher Aristotle's ideas about the universe reigned supreme. His influence was so profound that his theories shaped the way people understood the cosmos for nearly 2 millennia. Aristotle's works were studied, revered, and accepted as the ultimate truth about the natural world. Aristotle believed in a universe where everything had its natural place. This concept was central to his philosophy and was reflected in his views on the cosmos, motion, and the elements. He envisioned a harmonious universe where every object and being had a specific role and position. He thought that the Earth was the center of the cosmos and everything else revolved around it. This geocentric model placed our planet at the heart of the universe, with the sun, moon, stars, and planets orbiting around it in perfect circles. This idea was not just a scientific theory, but also a philosophical and theological one, aligning with the belief that humanity held a special place in the cosmos. Aristotle's ideas about motion were equally influential. He proposed that objects moved in specific ways depending on their nature and the elements they were composed of. His theories on motion were detailed in his works, which became foundational texts for centuries. He believed that objects had a natural tendency to be at rest. This meant that unless acted upon by an external force, objects would remain stationary. This idea was based on his observations of the natural world, where most objects seemed to stay put unless something moved them. To make an object move, you needed to apply a force to it. Aristotle's concept of force was straightforward. It was the push or pull that caused an object to change its state of motion. This idea was intuitive and matched everyday experiences where effort was required to move things. Once you stopped pushing or pulling, the object would naturally return to its state of rest. This observation led Aristotle to conclude that rest was the natural state of all objects, and motion was an unnatural state that required continuous force to maintain. Imagine a heavy rock sitting on the ground. To Aristotle, this was a perfect example of an object in its natural state. The rock, composed of the elements earth and water, was at rest because that was its natural tendency. To Aristotle, this was perfectly natural. The rock's position on the ground was a reflection of its inherent properties and the natural order of the universe. This idea extended to all objects, each having a natural place and state. The rock was made of earth and water, so its natural tendency was to be at rest on the ground. Aristotle's theory of the elements explained that each element had a natural place. Earth and water moved downward, while air and fire moved upward. This explained why rocks, being heavy and composed of earth, stayed on the ground. To lift the rock, you had to overcome its natural tendency by applying force. This required effort and energy, which Aristotle saw as a disruption of the rock's natural state. The need for force to move objects was a key part of his understanding of motion. Aristotle's ideas made sense based on everyday observations. People saw objects at rest and noticed that it took effort to move them. These observations reinforced Aristotle's theories, making them widely accepted and taught for generations. However, as we'll see, a revolution in scientific thought was about to unfold, challenging these long-held beliefs. The advent of new scientific methods and discoveries would eventually overturn Aristotle's ideas, leading to a new understanding of the universe and motion. This shift marked the beginning of modern science, where empirical evidence and experimentation became the cornerstones of knowledge. Galileo Galilei, an Italian astronomer and physicist, dared to question Aristotle's ideas about motion. Born in 1564 in Pisa, Italy, Galileo's curiosity and innovative thinking led him to challenge the long-held beliefs of his time. Galileo was a true scientific revolutionary. His work laid the foundation for modern physics and astronomy. He was not just a thinker, but a doer, someone who believed in the power of empirical evidence. He believed in the power of observation and experimentation. Instead of just accepting what ancient authorities claimed, Galileo wanted to see for himself how the world worked. This approach was radical at the time, as it emphasized the importance of direct observation and experimentation over philosophical speculation. One of Galileo's most famous experiments involved dropping objects from the Leaning Tower of Pisa. This experiment was designed to test Aristotle's theory that heavier objects fall faster than lighter ones. Legend has it that Galileo dropped two objects of different masses from the tower to see which would hit the ground first. According to the story, both objects hit the ground at the same time, contradicting Aristotle's teachings. While the story of the Leaning Tower experiment might be apocryphal, Galileo did conduct rigorous experiments with inclined planes to study the motion of falling objects. These experiments were crucial in developing his understanding of gravity and motion. Galileo carefully rolled balls down ramps of varying slopes. By doing so, he could slow down the motion enough to make precise measurements and observations. He meticulously measured the time it took for the balls to reach the bottom. Using rudimentary timekeeping devices like water clocks and his own pulse, Galileo was able to gather accurate data. What he discovered was groundbreaking. Contrary to Aristotle's beliefs, Galileo found that objects of different masses, when dropped from the same height, fall at the same rate, neglecting air resistance. This was a monumental shift in understanding, paving the way for Newton's laws of motion and the universal law of gravitation. Galileo's meticulous notes and observations were revolutionary. He documented his findings in a way that could be replicated and verified by others, a cornerstone of the scientific method. His work sparked debates and discussions among scholars and scientists of his time. Galileo's insistence on empirical evidence over accepted doctrine challenged the status quo and laid the groundwork for modern scientific inquiry. Beyond his experiments with gravity, Galileo also made significant contributions to astronomy. His improvements to the telescope allowed him to make unprecedented observations of the heavens, including the moons of Jupiter and the phases of Venus. Despite his groundbreaking discoveries, Galileo faced significant opposition from the Catholic Church. His support for the heliocentric model of the solar system, which placed the sun at the center rather than the Earth, led to his trial and house arrest. Galileo's legacy lives on today. His commitment to observation, experimentation, and challenging established beliefs continues to inspire scientists around the world. His work laid the foundation for the scientific revolution and transformed our understanding of the natural world. Galileo's experiments had profound implications for our understanding of motion. They directly challenged Aristotle's long-held and widely accepted beliefs. If objects of different masses fall at the same rate, then their natural tendency couldn't be to remain at rest. There had to be something else at play in the universe. Galileo's work laid the foundation for a new understanding of motion. He showed that objects in motion tend to stay in motion unless acted upon by an external force. This concept would later become known as inertia, a fundamental principle in physics. Galileo's experiments were not just about proving Aristotle wrong, they were about uncovering fundamental truths about the universe. His work paved the way for Sir Isaac Newton, who would build upon Galileo's insights to develop his groundbreaking laws of motion. Sir Isaac Newton, an English physicist and mathematician, is considered one of the most influential scientists of all time. His contributions to science laid the groundwork for many of the principles we understand today. Newton's work transcended the boundaries of his era, and his theories continue to be a cornerstone in the field of physics. Newton's three laws of motion, published in his masterpiece, Philosophiae Naturalis Principia Mathematica, often referred to simply as the Principia in 1687, revolutionized our understanding of the physical world. This monumental work not only provided a comprehensive framework for classical mechanics, but also laid the foundation for future scientific inquiry. Newton's first law of motion states that an object at rest stays at rest, and an object in motion stays in motion with the same speed and in the same direction unless acted upon by an unbalanced force. This principle is often summarized by the phrase, an object in motion stays in motion, and an object at rest stays at rest. This is the concept of inertia that Galileo had first explored. Galileo's experiments with rolling balls on inclined planes were crucial in developing the idea that objects resist changes to their state of motion. Imagine a spaceship coasting through the vast emptiness of space. In the vacuum of space, there are no air molecules to create resistance, and the gravitational forces are minimal unless the spaceship is near a massive object like a planet or a star. With no air resistance or gravity to slow it down, the spaceship will continue traveling in a straight line at a constant speed forever, unless acted upon by a force such as a gravitational pull from a nearby planet or a blast from its thrusters. This scenario perfectly illustrates Newton's first law in action. Newton's first law tells us that objects have a natural tendency to resist changes in their state of motion. This resistance is not just a theoretical concept, but something we experience in our daily lives. For instance, when you push a heavy piece of furniture, it resists your efforts to move it. This resistance to change is what we call inertia. Inertia is a property of matter that quantifies how much an object resists changes to its motion. The more massive an object, the greater its inertia, and the more force it takes to change its state of motion. This is why a truck is harder to start or stop moving than a bicycle. On a microscopic level, inertia is related to the mass of the atoms and molecules that make up an object. The more mass an object has, the more inertia it possesses. This is why lifting a heavy weight requires more effort than lifting a light one. Newton's exploration of inertia and motion has had a lasting impact on science and engineering. His laws of motion are still taught in classrooms around the world and are fundamental to our understanding of how objects move and interact. From the movement of celestial bodies to the engineering of spacecraft, Newton's first law of motion continues to be a guiding principle. It helps scientists and engineers design everything from cars to rockets, ensuring that we can predict and control the motion of objects in a variety of environments. Understanding inertia and the nature of motion is not just for scientists and engineers, it's a fundamental concept that helps us make sense of the world around us. Whether you're driving a car, playing sports, or simply walking, Newton's first law is at work, governing the motion of everything in our daily lives. So the next time you observe an object in motion or at rest, remember the principle of inertia. It's a reminder of the profound insights that Sir Isaac Newton provided, insights that continue to shape our understanding of the universe. Summary of Chapter 2 from A Brief History of Time by Stephen Hawking. Key concepts: Aristotle versus Galileo and Newton. Aristotle believed in a natural state of rest for objects with movement requiring a force. He thought heavier objects would fall faster. Galileo and Newton demonstrated that all objects fall at the same rate in the absence of air resistance, leading to Newton's laws of motion. Galileo's experiments showed acceleration due to gravity was constant, leading to Newton's first law of inertia and second law of acceleration. Newton's laws of motion and gravity. First law: an object will remain at rest or in uniform motion in a straight line unless acted upon by a force. Second law: the rate of change in momentum of an object is proportional to the applied force and inversely proportional to the mass of the object, gravity. Newton's law states that every point mass attracts every other point mass by a force acting along the line intersecting both points. The force is proportional to the product of the two masses and inversely proportional to the square of the distance. Relativity. Special relativity. Introduce the idea that the speed of light is constant for all observers regardless of their relative motion. This led to the concept of time dilation and mass energy. Proposed that gravity is not a force, but rather this theory explains the phenomenon like a daily space. Space and time are interwoven into the four-dimensional events described as four coordinates. Like illustrate how events can influence each other only if they lie within each other's feet or past light zones, highlighting the relativity of simultaneity and causality. Implications and experimental confirmation. Mercury's orbit. General relativity predicted the precession of Mercury's orbit, which was observed and confirmed. Light deflection predicted and observed during solar eclipses, confirming that light paths are bent by gravity. Time dilation. bodies, confirmed through experiments with clocks at different altitudes on Earth, showing that time runs slower closer to a massive body like Earth. Philosophical and practical outcomes. End of absolute time and space. Relativity eliminated the notion of universal, absolute time, showing that time and space are relative to the observer's frame of reference. Navigational systems. Modern GPS systems must account for relativistic effects to provide accurate positioning. This chapter fundamentally changes our understanding of physical laws, moving from a static view of the universe to a dynamic one where space and time are malleable. Here is a continuation of the concepts outlined in Chapter 2 of Stephen Hawking's A Brief History of Time. Further exploration of relativity, the twin towers. Explanation. One twin travels near the speed of light, while the other stays on Earth. The traveling twin would age slower due to time dilation effect. This isn't truly a paradox, but rather a demonstration of relativity's implications. The paradox resolves when considering that the travelling twin changes frame of reference accelerating around, experiencing different gravity and velocity effects. Space-time curve, general relativity. Planets orbit not the direction follow. These are the paths that minimize distance. Cosmological implications. Dynamic universe. Before general relativity, space and time were seen as an unchanging backdrop. Einstein's theory introduced a universe where space and time could expand or contract, leading to concepts like the Big Bang theory, cosmic expansion. The theory suggested that the universe could expand from a singularity, as later evidenced by Edwin Hubble's observations of redshift in distant galaxies. Hawking's contribution, singularity. Theorems, with Roger Penrose. Hawking proved that under certain conditions, general relativity predicts singularities, where the curvature of space-time becomes infinite, like in black holes or at the beginning of the universe. Big Bang. Experimental verification and modern applications. Gravitational waves predicted by general relativity and detected in 2015 by LIGO, confirming the theory's predictions about the dynamic nature of space-time. GPS and relativity. GPS satellites must correct for both special, due to their velocity, and general relativity effects, due to their altitude, to maintain accuracy. Philosophical shifts. From static to dynamic, the shift from a static, eternal universe to one with a definite beginning and potentially an end fundamentally altered philosophical and scientific views on existence and cosmology. Interconnectivity of space and time demonstrates how events in one part of the universe can influence others through the curvature of space-time, challenging previous notions of causality and simultaneity. Conclusion. This chapter in Hawking's book not only recounts the historical development of our understanding of space, time, and gravity, but also sets the stage for modern cosmology by introducing the revolutionary concept of relativity. It transitions from classical mechanics to a more nuanced view where the very fabric of reality is shaped by matter and energy, leading directly into discussions about the universe's origin, structure, and potential fate in subsequent chapters. Continue answer. Apologies for the typo in your request. Here's the continuation. Further implications and developments. Curvature of space. Types of curvature. General relativity allows for 3 types of spatial curvature based on the mass-energy content of the universe: positive, like a sphere; negative, like a saddle; or flat. Each type predicts different cosmic futures: closed, open, or flat universe, respectively. Black holes. Formation. Black holes are regions where gravity is so strong that nothing, not even light, can escape. They are one of the most dramatic consequences of general relativity, forming from the collapse of massive stars. Event horizon, the boundary beyond which escape is impossible. It represents the ultimate limit of our observable universe from within. Time travel and wormholes. Theoretical possibilities. General relativity allows for solutions like wormholes, which could theoretically connect distant parts of the universe or even different times. However, these require exotic matter with negative energy density, something not yet observed. Time travel, while solutions to Einstein's equations suggest time travel might be possible under certain conditions, like near black holes or through wormholes, practical and paradox issues make this highly speculative. Cosmic microwave background radiation, evidence for Big Bang. The discovery of the cosmic microwave background radiation in 1965 provided strong evidence for the Big Bang theory, which is rooted in the idea of an expanding universe from general relativity. Dark matter and dark energy. Dark matter. Observations suggest that visible matter alone cannot account for the observed gravitational effects in galaxies and clusters, leading to the hypothesis of dark matter, which interacts gravitationally but not electromagnetically. Dark energy. The accelerating expansion of the universe points to the existence of dark, a repulsive force or property of space itself, which could be explained within the framework of general relativity with modifications or new physics. Gravitational lensing. Observation. Light from distant objects is bent by intervening mass, providing a natural telescope. This not only confirms general relativity, but also has been used to map dark matter distributions. Quantum mechanics and gravity. Unification. Despite the success of general relativity, it conflicts with quantum mechanics at very small scales or in conditions like inside black holes. This has spurred efforts to create a quantum theory of gravity which might resolve these discrepancies. Hawking radiation quantum effects. Stephen Hawking proposed that black holes emit radiation due to quantum effects near the event horizon, leading to the concept that black holes could eventually evaporate over vast timescales, connecting general relativity with quantum mechanics. Philosophical and cultural impact. Redefining reality. Concepts introduced by relativity have not only changed science, but also philosophy, literature, and our cultural understanding of time, space, and causality. End of determinism. With quantum mechanics' probabilistic nature, the unpredictability introduced by chaotic systems. Classical. This chapter and the subsequent developments in physics illustrate how deeply intertwined our understanding of the cosmos is with the theories of relativity, pushing forward both theoretical and practical science into new realms of inquiry and application. Continue. Answer. Here's a further exploration of the topics and implications from Chapter 2 of A Brief History of Time. Advanced concepts and modern developments. Cosmological constant. Einstein's introduction. Originally introduced by Einstein to achieve a static universe model, he later discarded it as my greatest blunder when the expansion of the universe was discovered. However, with the discovery of dark energy, the cosmological constant has been resurrected as a possible explanation for the universe's accelerated expansion. Modern interpretation. Now it's viewed as a form of dark energy, providing a repulsive force that counteracts gravity on a cosmic scale. Inflation theory, early universe. Inflation suggests that the universe underwent a rapid expansion phase shortly after the Big Bang, smoothing out initial irregularities and explaining the large-scale homogeneity and isotropy observed in the cosmic microwave background. Connection to relativity. This theory modifies general relativity to account for this early expansion, suggesting that the very physics of space-time changed in the first moments of the universe. String theory and M-theory, unification efforts. These theories attempt to reconcile general relativity with quantum mechanics by proposing that particles are not point-like, but rather one-dimensional strings vibrating at specific frequencies. M-theory extends this into 11 dimensions, potentially offering a framework for a theory of everything. Gravitational waves, direct detection. The 2015 detection of gravitational waves by LIGO confirmed another prediction of general relativity, providing a new tool for observing cosmic events, like mergers of black holes or neutron stars, which are invisible in traditional electromagnetic observations. Frame dragging, lens-thirring effect. Rotational influence. General relativity predicts that rotating bodies drag space-time around with them. This effect was measured by the Gravity Probe B satellite, further confirming the theory's prediction about how mass influences the fabric of space-time. Quantum gravity. Loop. Quantum gravity. an approach where space-time is quantized into discrete chunks, attempting to merge quantum mechanics with general relativity without the need for them. Challenge. The quest for a consistent theory of quantum gravity remains one of the central challenges, with implications for understanding singularities and the earth. Multiverse theory, implications for relativity. Some interpretations of general relativity in quantum mechanics suggest the possibility of multiple universes or bubbles, each with different physical laws, explaining why our universe seems highly tuned. Experimental relativity tested in space. The European Space Agency's ACES, Atomic Clock Ensemble in Space project, aims to test general relativity with unprecedented precision by using clocks in space, looking into effects like gravitational redshift and time dilation. Black hole information paradox. Hawking's contribution. The paradox arises because quantum mechanics implies information should be conserved. But if a black hole evaporates completely via Hawking radiation, where does this information go? This still unresolved issue touches on the very nature of information, space-time, and quantum mechanics. The future of relativity. Further testing. Future experiments, possibly involving advanced telescopes, interferometers, or even space-based gravity wave detectors, will continue to test general relativity in new regimes, potentially leading to modifications or extensions of the theory. Cultural and educational impact. Public understanding of works like Hawking significantly influenced public interest, making complex ideas more accessible and sparking widespread fascination with the cosmos. Educational. The teaching of physics has evolved to include the concept often This chapter have not only shaped our scientific landscape, but also how we perceive time and the potential futures of both science and humanity. Continue answer. Here's an expansion on the implications and ongoing developments from Chapter 2 of A Brief History of Time. Philosophical and theoretical frontiers, the arrow of time, time's direction. General relativity does not inherently differentiate between past and future, but when combined with thermodynamics, it helps explain why time seems to have a direction, the increase in entropy. This leads to discussions about the nature of time, free will, and causality. The holographic principle, information storage. This principle suggests that the information contained in a volume of space can be described by a theory on its boundary, much like a hologram. It's a profound idea that could help reconcile quantum mechanics with general relativity, suggesting our 3D universe might be a projection from a 2D surface. Time travel paradoxes, causality and loops. General relativity allows for theoretical scenarios where time travel might be possible, leading to paradoxes like the grandfather paradox. Theoretical frameworks like the Novikov self-consistency principle propose that any actions taken by a time traveler were always part of history, preventing paradoxes. Cosmic censorship hypotheses, singularities. Proposed by Roger Penrose, these hypotheses suggest that singularities, like those at the center of black holes, are always hidden from outside observers by event horizons, preserving the predictability of general relativity. Technological and observational advances, precision in navigation, GPS and relativity. The daily use of GPS provides a practical demonstration of relativity. Every GPS satellite must account for both the time dilation effects due to their velocity, special relativity, and their height above Earth's surface, general relativity, to provide accurate location services. Future space missions, gravitational testing. Missions like ESA's LISA, Laser Interferometer Space Antenna, aim to detect gravitational waves with much higher sensitivity than ground-based detectors, potentially observing events from the early universe or testing general relativity in new ways. Quantum computing and relativity, quantum simulation. There's growing interest in using quantum computers to simulate gravitational effects or even black holes, potentially offering insights into conditions where traditional computers fail due to computational complexity. Philosophical and cultural reflections. Humanity's place in the universe. cosmic perspective, the understanding of relativity and the expanding universe, has shifted humanity's view from being central in a static cosmos to one of many possible configurations in an evolving universe, impacting philosophy, religion, and existential thought. Time and experience. Relativity in literature. Concepts from relativity have influenced literature and art, exploring themes of time, identity, and the fluidity of reality, as seen in works by authors like Jorge Luis Borges or films like Interstellar. Education and public engagement. Cosmology for all. The simplification and dissemination of complex ideas like relativity through popular science books, documentaries, and educational platforms have democratized science, fostering a culture of curiosity and learning. The ongoing quest for understanding, unification of forces. The dream of a unified theory that includes gravity with the other fundamental forces remains elusive. Advances in particle physics, particularly at facilities like the Large Hadron Collider, continue to probe for new physics that might hint at this unification. Interdisciplinary approaches, physics, astronomy, philosophy, and even psychology converge in discussions about the nature of time, space, and consciousness, reflecting how deeply ingrained these concepts are in human culture and cognition. Ethical and philosophical implications. As our understanding of the universe expands, so do questions about the ethics of space exploration, the implications of time travel or alternate realities, and the responsibility of humanity in an increasingly understood cosmos. This chapter in Hawking's narrative is not just a recount of scientific history, but a catalyst for ongoing curiosity, research, and philosophical discourse about our place in the universe. It underscores the dynamic interplay between theory, observation, and the human quest for knowledge. Space and time. Our present ideas about the motion of bodies date back to Galileo and Newton. Before them, people believed Aristotle, who said that the natural state of a body was to be at rest and that it moved only if driven by a force or impulse. It followed that a heavy body should fall faster than a light one because it would have a greater pull toward the earth. The Aristotelian tradition also held that one could work out all the laws that govern the universe by pure thought. It was not necessary to check by observation. So no one until Galileo bothered to see whether bodies of different weight did in fact fall at different speeds. It is said that Galileo demonstrated that Aristotle's belief was false by dropping weights from the Leaning Tower of Pisa. The story is almost certainly untrue, but Galileo did do something equivalent. He rolled balls of different weights down a smooth slope. The situation is similar to that of heavy bodies falling vertically, but it is easier to observe because the speeds are smaller. Galileo's measurements indicated that each body increased its speed at the same rate, no matter what its weight. For example, if you let go of a ball on a slope that drops by 1 meter for every 10 meters you go along, the ball will be traveling down the slope at a speed of about 1 meter per second after 1 second, 2 meters per second after 2 seconds, and so on, however heavy the ball. Of course, a lead weight would fall faster than a feather, but that is only because a feather is slowed down by air resistance. If one drops two bodies that don't have much air resistance, such as two different lead weights, they fall at the same rate. On the Moon, where there is no air to slow things down, the astronaut David R. Scott performed the feather and lead weight experiment and found that indeed they did hit the ground at the same time. Galileo's measurements were used by Newton as the basis of his laws of motion. In Galileo's experiments, as a body rolled down the slope, it was always acted on by the same force, its weight, and the effect was to make it constantly speed up. This showed that the real effect of a force is always to change the speed of a body rather than just to set it moving, as was previously thought. It also meant that whenever a body is not acted on by any force, it will keep on moving in a straight line at the same speed. This idea was first stated explicitly in Newton's Principia Mathematica, published in 1687, and is known as Newton's first law. What happens to a body when a force does act on it is given by Newton's second law. This states that the body will accelerate or change its speed at a rate that is proportional to the force. For example, the acceleration is twice as great if the force is twice as great. The acceleration is also smaller, the greater the mass, or quantity of matter, of the body. The same force acting on a body of twice the mass will produce half the acceleration. A familiar example is provided by a car. The more powerful the engine, the greater the acceleration, but the heavier the car, the smaller the acceleration for the same engine. In addition to his laws of motion, Newton discovered a law to describe the force of gravity, which states that every body attracts every other body with a force that is proportional to the mass of each body. Thus, the force between two bodies would be twice as strong if one of the bodies, say body A, had its mass doubled. This is what you might expect because one could think of the new body A as being made of two bodies with the original mass. Each would attract body B with the original force. Thus, the total force between A and B would be twice the original force, and if, say, one of the bodies had twice the mass and the other had 3 times the mass, then the force would be 6 times as strong. One can now see why all bodies fall at the same rate. A body of twice the weight will have twice the force of gravity pulling it down, but it will also have twice the mass. According to Newton's second law, these two effects will exactly cancel each other, so the acceleration will be the same in all cases. Newton's law of gravity also tells us that the farther apart the bodies, the smaller the force. Newton's law of gravity says that the gravitational attraction of a star is exactly 1/4 that of a similar star at half the distance. This law predicts the orbits of the Earth, the Moon and the planets with great accuracy. If the law were that the gravitational attraction of a star went down faster or increased more rapidly with distance, the orbits of the planets would not be elliptical. They would either spiral into the Sun or escape from the Sun. The big difference between the ideas of Aristotle and those of Galileo and Newton is that Aristotle believed in a preferred state of rest, which anybody would take up if it were not driven by some force or impulse. In particular, he thought that the Earth was at rest. But it follows from Newton's laws that there is no unique file://c vertical bar /windows /desktop /blah /Stephen Hawking, a brief history of time /a.html, 1 of 12, February 20th, 2001, 3 hours, 14 minutes and 15 seconds. AM, a brief history of time, Stephen Hawking. Chapter 2, Standard of rest. One could equally well say that body A was at rest and body B was moving at constant speed with respect to body A, or that body B was at rest and body A was moving. For example, if one sets aside for a moment the rotation of the Earth and its orbit round the Sun, one could say that the Earth was at rest and that a train on it was travelling north at 90 miles per hour, or that the train was at rest and the Earth was moving south at 90 miles per hour. If one carried out experiments with moving bodies on the train, all Newton's laws would still hold. For instance, playing ping pong on the train, one would find that the ball obeyed Newton's laws, just like a ball on a table by the track. So there's no way to tell whether it is the train or the Earth that is moving. The lack of an absolute standard of rest meant that one could not determine whether two events that took place at different times occurred in the same position in space. For example, suppose our ping pong ball on the train bounces straight up and down, hitting the table twice on the same spot 1 second apart. To someone on the track, the two bounces would seem to take place about 40 meters apart, because the train would have traveled that far down the track between the bounces. The non-existence of absolute rest therefore meant that one could not give an event an absolute position in space, as Aristotle had believed. The positions of events and the distances between them would be different for a person on the train and one on the track, and there would be no reason to prefer one person's position to the other's. Newton was very worried by this lack of absolute position, or absolute space as it was called, because it did not accord with his idea of an absolute God. In fact, he refused to accept lack of absolute space, even though it was implied by his laws. He was severely criticized for this irrational belief by many people, most notably by Bishop Berkeley, a philosopher who believed that all material objects and space and time are an illusion. When the famous Dr. Johnson was told of Berkeley's opinion, he cried, "I refute it thus," and stubbed his toe on a large stone. Both Aristotle and Newton believed in absolute time. That is, they believed that one could unambiguously measure the interval of time between two events, and that this time would be the same whoever measured it, provided they used a good clock. Time was completely separate from and independent of space. This is what most people would take to be the common sense view. However, we've had to change our ideas about space and time. Although our apparently common sense notions work well when dealing with things like apples or planets that travel comparatively slowly, they don't work at all for things moving at or near the speed of light. The fact that light travels at a finite but very high speed was first discovered in 1676 by the Danish astronomer Ole Christensen Romer. He observed that the times at which the moons of Jupiter appeared to pass behind Jupiter were not evenly spaced, as one would expect if the moons went round Jupiter at a constant rate. As the Earth and Jupiter orbit around the Sun, the distance between them varies. Romer noticed that eclipses of Jupiter's moons appeared later the farther we were from Jupiter. He argued that this was because the light from the moons took longer to reach us when we were farther away. His measurements of the variations in the distance of the Earth from Jupiter were, however, not very accurate, and so his value for the speed of light was 140,000 miles per second compared to the modern value of 186,000 miles per second. Nevertheless, Romer's achievement in not only proving that light travels at a finite speed, but also in measuring that speed was remarkable, coming as it did 11 years before Newton's publication of Principia Mathematica. A proper theory of the propagation of light didn't come until 1865, when the British physicist James Clerk Maxwell succeeded in unifying the partial theories that up to then had been used to describe the forces of electricity and magnetism. Maxwell's equations predicted that there could be wave-like disturbances in the combined electromagnetic field, and that these would travel at a fixed speed, like ripples on a pond. If the wavelength of these waves, the distance between one wave crest and the next, is a meter or more, they are what we now call radio waves. Shorter wavelengths are known as microwaves, a few centimeters, or infrared, more than a 10,000th of a centimeter. Visible light has a wavelength of between only 40 and 80 millionths of a centimeter. Even shorter wavelengths are known as ultraviolet, X-rays and gamma rays. Maxwell's theory predicted that radio or light waves should travel at a certain fixed speed. But Newton's theory had got rid of the idea of absolute rest. So if light was supposed to travel at a fixed speed, one would have to say what that fixed speed was to be measured relative to. It was therefore suggested that there was a substance called the ether that was present everywhere, even in empty space. Light waves should travel through the ether as sound waves travel through air, and their speed should therefore be relative to the ether. Different observers moving relative to the ether would see light file : //c vertical bar / windows / desktop / blah / Stephen Hawking. A Brief History of Time /a.html 2 of 12, February 20th, 2001, 3 hours, 14 minutes and 15 seconds. AM, A Brief History of Time, Stephen Hawking, Chapter 2. Coming toward them at different speeds, but light speed relative to the ether would remain fixed. In particular, as the Earth was moving through the ether on its orbit round the Sun, the speed of light measured in the direction of the Earth's motion through the ether, when we were moving toward the source of the light, should be higher than the speed of light at right angles to that motion, when we are not moving toward the source. In 1887, Albert Michelson, who later became the first American to receive the Nobel Prize for Physics, and Edward Morley carried out a very careful experiment at the Case School of Applied Science in Cleveland. They compared the speed of light in the direction of the Earth's motion with that at right angles to the Earth's motion. To their great surprise, they found they were exactly the same. Between 1887 and 1905, there were several attempts, most notably by the Dutch physicist Hendrik Lorentz, to explain the result of the Michelson-Morley experiment in terms of objects contracting and clocks slowing down when they moved through the ether. However, in a famous paper in 1905, a hitherto unknown clerk in the Swiss Patent Office Albert Einstein, pointed out that the whole idea of an ether was unnecessary, providing one was willing to abandon the idea of absolute time. A similar point was made a few weeks later by a leading French mathematician, Henri Poincaré. Einstein's arguments were closer to physics than those of Poincaré, who regarded this problem as mathematical. Einstein is usually given the credit for the new theory, but Poincaré is remembered by having his name attached to an important part of it. The fundamental postulate of the theory of relativity, as it was called, was that the laws of science should be the same for all freely moving observers, no matter what their speed. This was true for Newton's laws of motion, but now the idea was extended to include Maxwell's theory and the speed of light. All observers should measure the same speed of light, no matter how fast they are moving. This simple idea has some remarkable consequences. Perhaps the best known are the equivalents of mass and energy, summed up in Einstein's famous equation E equals sine mc2, where E is energy, m is mass, and c is the speed of light, and the law that nothing may travel faster than the speed of light. Because of the equivalence of energy and mass, the energy which an object has due to its motion will add to its mass. In other words, it will make it harder to increase its speed. This effect is only really significant for objects moving at speeds close to the speed of light. For example, at 10% of the speed of light, an object's mass is only 0.5% more than normal, while at 90% of the speed of light, it would be more than twice its normal mass. As an object approaches the speed of light, its mass rises ever more quickly, so it takes more and more energy to speed it up further. It can in fact never reach the speed of light, because by then its mass would have become infinite, and by the equivalence of mass and energy, it would have taken an infinite amount of energy to get it there. For this reason, any normal object is forever confined by relativity to move at speeds slower than the speed of light. Only light, or other waves that have no intrinsic mass, can move at the speed of light. An equally remarkable consequence of relativity is the way it has revolutionized our ideas of space and time. In Newton's theory, if a pulse of light is sent from one place to another, different observers would agree on the time that the journey took, since time is absolute, but will not always agree on how far the light traveled, since space is not absolute. Since the speed of the light is just the distance it has traveled divided by the time it has taken, different observers would measure different speeds for the light. In relativity, on the other hand, all observers must agree on how fast light travels. They still, however, do not agree on the distance the light has traveled, so they must therefore now also disagree over the time it has taken. The time taken is the distance the light has traveled, which the observers do not agree on, divided by the light's speed, which they do agree on. In other words, the theory of relativity put an end to the idea of absolute time. It appeared that each observer must have his own measure of time, as recorded by a clock carried with him, and that identical clocks carried by different observers would not necessarily agree. Each observer could use radar to say where and when an event took place by sending out a pulse of light or radio waves. Part of the pulse is reflected back at the event, and the observer measures the time at which he receives the echo. The time of the event is then said to be the time halfway between when the pulse was sent and the time when the reflection was received back. The distance of the event is half the time taken for this round trip, multiplied by the speed of light. An event in this sense is something that takes place at a single point in space, at a specified point in time. This idea is shown here, which is an example of a space-time diagram. file://c /windows/desktop/blah/Stephen Hawking, a brief history of time/a.html 3 of 12, February 20th, 2001, 3 hours, 14 minutes and 16 seconds AM, a brief history of time, Stephen Hawking. Chapter 2. Figure 2. Using this procedure, observers who are moving relative to each other will assign different times and positions to the same event. No particular observer's measurements are any more correct than any other observer's, but all the measurements are related. Any observer can work out precisely what time and position any other observer will assign to an event, provided he knows the other observer's relative velocity. Nowadays, we use just this method to measure distances precisely, because we can measure time more accurately than length. In effect, the meter is defined to be the distance travelled by light in 0.0000003333564095 second, as measured by a cesium clock. The reason for that particular number is that it corresponds to the historical definition of the meter in terms of 2 marks on a particular platinum bar kept in Paris. Equally, we can use a more convenient new unit of length called a light second. This is simply defined as the distance that light travels in 1 second. In the theory of relativity, we now define distance in file ://c vertical bar /windows /desktop /blah /Stephen Hawking. A brief history of time /a.html. February 22, 3 hours 14 minutes and 16 seconds. AM. A brief history of time. Chapter 2. Terms of time and speed of light. So it follows automatically that every observer will measure light to have the same speed. By definition, 1 meter. 0.0000003333564095 second. There is no need to introduce the idea of an ether, whose presence anyway cannot be detected, as the Michelson-Morley experiment showed. The theory of relativity does, however, force us to change fundamentally our ideas of space and time. We must accept that time is not completely separate from and independent of space, but is combined with it to form an object called space-time. It is a matter of common experience that one can describe the position of a point in space by 3 numbers or coordinates. For instance, one can say that a point in a room is 7 feet from one wall, 3 feet from another, and 5 feet above the floor. Or one could specify that a point was at a certain latitude and longitude and a certain height above sea level. One is free to use any 3 suitable coordinates, although they have only a limited range of validity. One would not specify the position of the moon in terms of miles north and miles west of Piccadilly Circus and feet above sea level. Instead, one might describe it in terms of distance from the sun, distance from the plane of the orbits of the planets, and the angle between the line joining the moon to the sun and the line joining the sun to a nearby star such as Alpha Centauri. Even these coordinates would not be of much use in describing the position of the sun in our galaxy or the position of our galaxy in the local group of galaxies. In fact, one may describe the whole universe in terms of a collection of overlapping patches. In each patch, one can use a different set of 3 coordinates to specify the position of a point. An event is something that happens at a particular point in space and at a particular time, so one can specify it by 4 numbers or coordinates. Again, the choice of coordinates is arbitrary. One can use any 3 well-defined spatial coordinates and any measure of time. In relativity, there is no real distinction between the space and time coordinates, just as there is no real difference between any 2 space coordinates. One could choose a new set of coordinates in which, say, the first space coordinate was a combination of the old first and second space coordinates. For instance, instead of measuring the position of a point on the Earth in miles north of Piccadilly and miles west of Piccadilly, one could use miles northeast of Piccadilly and miles northwest of Piccadilly. Similarly, in relativity, one could use a new time coordinate that was the old time in seconds, plus the distance in light seconds north of Piccadilly. It is often helpful to think of the 4 coordinates of an event as specifying its position in a 4-dimensional space called spacetime. It is impossible to imagine a 4-dimensional space. I personally find it hard enough to visualize 3-dimensional space. However, it is easy to draw diagrams of 2-dimensional spaces, such as the surface of the Earth. The surface of the Earth is 2-dimensional because the position of the point can be specified by 2 coordinates, latitude and longitude. I shall generally use diagrams in which time increases upward and one of the spatial dimensions is shown horizontally. The other 2 spatial dimensions are ignored, or sometimes one of them is indicated by perspective. These are called space-time diagrams, like Figure 2.1, file ://c vertical bar /windows /desktop /blah /Stephen Hawking. A brief history of time /a.html, 5 of 12, February 20th, 2001. 3 hours, 14 minutes and 16 seconds AM. A brief history of time. Stephen Hawking. Chapter 2. Figure 2. 2, for example, in Figure 2, time is measured upward in years, and the distance along the line from the Sun to Alpha Centauri is measured horizontally in miles. The paths of the Sun and of Alpha Centauri through space-time are shown as the vertical lines on the left and right of the diagram. A ray of light from the Sun follows the diagonal line and takes 4 years to get from the Sun to Alpha Centauri. As we have seen, Maxwell's equations predicted that the speed of light should be the same whatever the speed of the source, and this has been confirmed by actual measurements. It follows from this that if the pulse of light is emitted at a particular time, then as time goes on, it will spread out in the sphere of light in size. The light will have spread out to form a sphere. 2 million. It will be like the ripples that spread out on the surface of a pond when a stone is thrown in. The ripples spread out as a circle that gets bigger as time goes on. If one stacks snapshots of the ripples at different times, one above the other, the expanding circle of ripples will mark out a cone whose tip is at the place and time at which the stone hit the water. Figure 2.3. File ://C, vertical bar /Windows /desktop /blah /Stephen Hawking. A brief history of time /A.html, 6 of 12. February 20th, 2001, 3 hours, 14 minutes and 16 seconds AM. A brief history of time, Stephen Hawking, Chapter 2. Figure 2.3. Similarly, the light spreading out from an event forms a three-dimensional cone in the four-dimensional space-time. This cone is called the future light cone of the event. In the same way, we can draw another cone called the past light cone, which is the set of events from which a pulse of light is able to reach the given event. Figure 2.4. File ://C, vertical bar /Windows /desktop /blah /Stephen Hawking. A brief history of time /A.html, 7 of 12. February 20th, 2001. 3 hours, 14 minutes and 16 seconds AM. A brief history of time, Stephen Hawking, Chapter 2. Figure 2.4. Given an event P, one can divide the other events in the universe into 3 classes. Those events that can be reached from the event P by a particle or wave traveling at or below the speed of light are said to be in the future of P. They will lie within or on the expanding sphere of light emitted from the event P. Thus, they will lie within or on the future light cone of P in the space-time diagram. Only events in the future of P can be affected by what happens at P because nothing can travel faster than light. Similarly, the past of P can be defined as the set of all events from which it is possible to reach the event P traveling at or below the speed of light. It is thus the set of events that can affect what happens at P. The events that do not lie in the future or past of P are said to lie in the elsewhere of P. Figure 2.5. File ://C, vertical bar /Windows /desktop /blah /Stephen Hawking. A brief history of time /A.html, 8 of 12. February 20th, 2001, 3 hours, 14 minutes and 16 seconds AM. A brief history of time, Stephen Hawking. Chapter 2. Figure 2.5. What happens at such events can neither affect nor be affected by what happens at P. For example, if the sun were to cease to shine at this very moment, it would not affect things on Earth at the present time because they would be in the elsewhere of the event when the sun went out. Figure 2.6. File ://C, vertical bar /Windows /desktop /blah /Stephen Hawking. A brief history of time /A.html, 9 of 12. February 20th, 2001, 3 hours, 14 minutes and 16 seconds AM. A brief history of time, Stephen Hawking. Chapter 2, Figure 2.6. We would know about it only after 8 minutes, the time it takes light to reach us from the sun. Only then would events on Earth lie in the future light cone of the event at which the sun went out. Similarly, we do not know what is happening at the moment farther away from the universe. The light that we see from distant galaxies left in millions of years ago. And in the case of the most distant object that we can see, the light left some 8,000 years ago. Thus, when we look at the universe, we are seeing it as it was in the past. If one neglects gravitational effects, as Einstein did in 1905, one has what is called the special theory of relativity. For every event in space-time, we may construct a light cone, the set of all possible paths of light in space-time permitted. And since the speed of light is the same at every event in every direction, all the light cones will be identical and will all point in the same direction. The theory also tells us that nothing can travel faster. This means that the path of any object in space and time must be represented within the light of each event. The special theory of describing what happens when things move at speed space. However, it was inconsistent with the Newtonian theory of gravity, which said that objects attracted each other with a force that depended on the distance between them. This meant that if one moved one of the objects, the force on the other one would change instantaneously. Or in other gravitational effects should travel with infinite velocity, instead of at or below the speed of light, as the special theory of relativity required. Einstein made a number of unsuccessful attempts between 1908 and 1914 to find a theory of gravity that was consistent with special relativity. Finally, in 1915, he proposed what we now call the general theory of relativity. Einstein made the revolutionary suggestion that gravity is not a force like other forces, but is a consequence of the fact that space-time is not flat, as had been previously assumed. It is curved or warped by the distribution file ://c, vertical bar /windows /desktop /blah/Stephen Hawking, a brief history of time /a.html 10 of 12, February 20th, 2001, 3 hours, 14 minutes and 16 seconds, AM, a brief history of time, Stephen Hawking, chapter 2 of mass and energy in it. Bodies like the Earth are not made to move on curved orbits by a force called gravity. Instead, they follow the nearest thing to a straight path in a curved space, which is called a geodesic. A geodesic is the shortest or longest path between two nearby points. For example, the surface of the Earth is a two-dimensional curved space. A geodesic on the Earth is called a great circle and is the shortest route between 2 points. Fig 2.8. As the geodesic is the shortest path between any two airports, this is the route an airline navigator will tell the pilot to fly along. In general relativity, bodies always follow straight lines in four-dimensional space-time, but they nevertheless appear to us to move along curved paths in our three-dimensional space. This is rather like watching an airplane flying over hilly ground. Although it follows a straight line in three-dimensional space, its shadow follows a curved path on the two-dimensional ground. The mass of the Sun curves space-time in such a way that although the Earth follows a straight path in four-dimensional space-time, it appears to us to move along a circular orbit in three-dimensional space. Fact: the orbits of the planets predicted by general relativity are almost exactly the same as those predicted by the Newtonian theory of gravity. However, in the case of Mercury, which, being the nearest planet to the Sun, feels the strongest gravitational effects and has a rather elongated orbit, general relativity predicts that the long axis of the ellipse should rotate about the Sun at a rate of about 1 degree in 10,000 years. Small though this effect is, it had been noticed before 1915 and served as one of the first confirmations of Einstein's theory. In recent years, the even smaller deviations of the orbits of the other planets from the Newtonian predictions have been measured by radar and found to agree with the predictions of general relativity. Light rays, too, must follow geodesics in space-time. Again, the fact that space is curved means that light no longer appears to travel in straight lines in space. So general relativity predicts that light should be bent by gravitational fields. For example, the theory predicts that the light cones of points near the Sun would be slightly bent inward on account of the mass of the Sun. This means that light from a distant star that happened to pass near the Sun would be deflected through a small angle, causing the star to appear in a different position to an observer on the Earth, Fig 2.9. Of course, if the light from the star always passed close to the Sun, we would not be able to tell whether the light had been deflected, or if instead the star was really where we see it. However, as the Earth orbits around the Sun, different stars appear to pass behind the Sun and have their light reflected. They therefore change their apparent position relative to other stars. It is normally very difficult to see this effect, because the light from the Sun makes it impossible to observe stars that appear near to the Sun in the sky. However, it is possible to do so during an eclipse of the Sun, when the Sun's light is blocked out by the Moon. Einstein's prediction of light deflection could not be tested immediately in 1915, because the First World War was in progress, and it was not until 1919 that a British expedition observing an eclipse from West Africa showed that light was indeed deflected by the Sun, just as predicted by the theory. This proof of a German theory by British scientists was hailed as a great act of reconciliation between the two countries after the war. It is ironic, therefore, that later examination of the photographs taken on that expedition showed the errors were as great as the effect they were trying to measure. Their measurement had been sheer luck, or a case of knowing the result they wanted to get, not an uncommon occurrence in science. The light deflection has, however, been accurately confirmed by a number of later observations. Another prediction of general relativity is that time should appear to slower near a massive body like the Earth. This is because there is a relation between the energy of light and its frequency, that is, the number of waves of light per second. The greater the energy, the higher frequency. As light travels upward in the Earth's gravitational field, it loses energy, and so its frequency goes down. This means that the length of time between one wave crest and the next goes up. To someone high up, it would appear that everything down below was making longer to happen. This prediction was tested in 1962 using a pair of very accurate clocks mounted at the top and bottom of a water tower. The clock at the bottom, which was nearer the Earth, was found to run slower in exact agreement with general relativity. The difference in the speed of clocks at different heights above the Earth is now of considerable practical importance, with the advent of very accurate navigation systems based on signals from satellites. If one ignored the predictions of general relativity, the position that one calculated would be wrong by several miles. Newton's laws of motion put an end to the idea of absolute position in space. The theory of relativity gets rid of absolute time. Consider a pair of twins. Suppose that one twin goes to live on the top of a mountain while the other stays at sea level. The first twin would age faster than the second. Thus, if they met again, one would be older than the other. In this case, the difference in ages would be very small, but it would be much larger if one file://c vertical bar /windows /desktop /blah /Stephen Hawking. A brief history of time/a.html 11 of 12. February 20th, 2001, 3 hours, 14 minutes and 16 seconds AM. A brief history of time. Stephen Hawking. Chapter 2 of the twins went for a long trip in a spaceship at nearly the speed of light. When he returned, he would be much younger than the one who stayed on Earth. This is known as the twins' paradox, but it is a paradox only if one has the idea of absolute time at the back of one's mind. In the theory of relativity, there is no unique absolute time, but instead each individual has his own personal measure of time that depends on where he is and how he is moving. Before 1915, space and time were thought of as a fixed arena in which events took place, but which was not affected by what happened in it. This was true even of the special theory of relativity. Bodies moved, forces attracted and repelled, but time and space simply continued unaffected. It was natural to think that space and time went on forever. The situation, however, is quite different in the general theory of relativity. Space and time are now dynamic quantities. When a body moves or a force acts, it affects the curvature of space and time, and in turn the structure of space-time affects the way in which bodies move and forces act. Space and time not only affect, but also are affected by everything that happens in the universe. Just as one cannot talk about events in the universe without the notions of space and time, so in general relativity, it became meaningless to talk about space and time outside the limits of the universe. In the following decades, this new understanding of space and time was to revolutionize our view of the universe. The old idea of an essentially unchanging universe that could have existed and could continue to exist forever was replaced by the notion of a dynamic, expanding universe that seemed to have begun a finite time ago and that might end at a finite time in the future. That revolution forms the subject of the next chapter. And years later, it was also to be the starting point for my work in theoretical physics. Roger Penrose and I showed that Einstein's general theory of relativity implied that the universe must have a beginning and, possibly, an end.